Hello, everybody, and thanks for tuning in. Today, I'm going to talk about recent progress that we have made as a community to build autonomous systems, but I'll also talk about challenges and argue why we haven't accomplished our final goal yet. From my own research, I will particularly share some recent trends and insights in how to make AI-enabled autonomous systems safe and reliable. First off, what are autonomous systems? Autonomous systems are engineered systems that operate in complex and open-ended environments. They perceive the environment, they reason and learn from data, and they act in order to achieve a wide variety of tasks to advance society and improve life for everyone. Autonomous systems research, in particular, promises to enable many future technologies, such as in the automotive industry, like self-driving cars, and also in manufacturing, healthcare, and in aerospace and robotics applications, but also in agriculture, connected cities, and automated services. And all of this certainly highlights the potential impact that autonomous systems research may have in the future. Over the past years, the wide availability of data, coupled with the computational advances in machine learning and AI, has really accelerated the progress that we have made in order to build fully autonomous systems. And I've shown some examples over here. I guess you all have seen Tesla cars, but also robots from Boston Dynamics, or I've shown here a drone fleet from the Kumar lab here at Penn. And in all of these demonstrations, you can see autonomous systems performing highly complex and challenging tasks with ease. And from these demonstrations, one could certainly argue that, yes, autonomous systems are a reality. However, the question that I would now like to ask is, do we really have all the theories and tools in hand to build autonomous systems that are also safe? And I would argue that the answer to this question is no, simply because at the same time, we have seen a lot of failed demonstrations. We've seen Boston Dynamics robots crashing, Tesla cars colliding, even endangering human lives, as well as drone fleets just crashing again. And from my own experience in the lab, I would even argue that for each successful video that you can find online, or as shown on the previous slide, there are at least 10 or more videos of failed experiments on the hard drives of the producers. So then the question becomes, how reliable and safe are these autonomous systems really? And I guess all of us had the hope, probably like in 2015, that by 2020, self-driving cars would be a reality. But as of today, this is really not the case. And even worse, the autonomous driving industry has reset their expectations to only level 4 autonomy, meaning fully autonomous systems only in certain controlled environments, for instance, at airports. And this has led researchers here, for instance, from MIT, to instead focus on more solvable problems, here, for instance, on autonomous boats. And there are a variety of reasons why we have such problems. One being that it seems that the way that we train our AI is fundamentally flawed, as we train and tweak our algorithms to lab-like environments, but don't make the transfer outside the lab. Another reason is that by now it's known that AI is really easy to fool because neural networks have shown to be not always robust. There's this famous example of a panda image that by an algorithm is correctly classified as a panda. But then if we put some small noise on top, the resulting picture really looks the same to the human eye at least, but the algorithm will suddenly classify it with high confidence as a given, right? So then the question for us is, how can we make AI-enabled autonomous systems safe and reliable, but also what are the fundamental limitations that we're facing, and what are the formal performance and safety guarantees that we can provide? Autonomous systems research that addresses these problems touches many research disciplines. It starts from the mechanical design, goes over to signal processing, computer vision, humans in the loop, distributed systems, communication, privacy and security issues, mission and task planning, system identification, dynamics and control, data and machine learning, as well as system verification. The point that I want to make here is simply that autonomous systems research is an interdisciplinary endeavor that requires researchers from different fields, so from mechanical engineering, electrical engineering, from computer science, as well as from applied math, to sit together and address these challenging problems. My own autonomous systems research agenda is a little more focused, of course. During my postdoc here at Penn, I've been working on data-driven control, and the first part of this talk will be on the topic of learning safe control laws from expert demonstrations. Also, during my postdoc year, I've worked on risk-aware autonomy. This is going to be the second part of today's talk, and I'm going to talk about how we can assess and verify risk of AI-enabled autonomous systems. I've also worked in my PhD at KDH on formal methods and control. So basically, how can we control and verify systems under complex mission specifications? And I've also worked on distributed autonomy. And more recently, and in the future, I also want to work on human-centered AI. I also want to briefly mention the 3 dimensions of my research that basically my research operates in. There's a system axis over here, along which the dynamics of the system become more complex and potentially more agents are involved. There's a specification axis here, starting from simple spatial specifications, for instance, collision avoidance specifications, and then going over to spatiotemporal specifications where timing plays a role, for instance, when deadlines are involved or temporal ordering of tasks. And on the last axis, there's an environment, really starting from known environments, going to unknown and dynamic environments, and then to environments where humans are in the loop. My PhD has been largely in this space, so simple systems, complex specifications, and known environments. The first part of this talk will be for complex systems, simple safety specifications, and in known and unknown environments. And the second part of today's talk will be for unknown environments, for complex systems and specifications. Lastly, I want to also briefly mention the tools that I'm using to address these challenges. I have a strong background in model-based control, particularly in nonlinear control, as well as in temporal logics and verifications. And I'm also using tools from machine learning and AI. And as you can imagine, as these circles are really isolated, I'm working at the intersection of them. One last thing I want to mention, in my research, robustness is really important. So I'm using robustness for several reasons. One being that it allows me to glue theories and tools from these circles here correctly together, but also obviously we're always interested in robustness to be robust against various forms of uncertainty. Okay, so let me jump into the first part of this talk, which is about learning safe control laws from expert demonstrations. Like I said, this is for complex systems, simple safety specifications, and known and unknown environments. And we're here at the intersection of control and machine learning and AI. I would now like to shift the focus again to safety critical systems, which are systems where failure of the system can have catastrophic consequences and basically result in property damage or even in the loss of human life. And unfortunately, we had to observe several of these incidents over the past years. Here, an Uber incident in which unfortunately a human being even died. Here, another example where drone collided with a commercial airplane and luckily no one got hurt. But the point that I want to make here is that when we're dealing with safety critical systems, safety is of course the most important thing. And we now want to focus on how can we design safe systems. A system is safe if its behavior is considered safe. And I want to now use a bit more of a control-ish language and say that a system is safe if we can control it to stay within a safe declared set C. So let's say we have a system that's the robot over here and our as safe declared set is the blue region here. Then our system is simply safe if it can operate freely within this region while never leaving the safe region, okay? Of course, a lot of people have worked on these problems. There are approaches to handcraft safe control laws. Of course, this is not really principled and often limited to simple systems without any safety guarantees. There are sum of squares programming approaches, Hamilton, Jacobi, Bellman, reachability analysis, as well as discrete program synthesis from the computer science community. But they all share the similarity that they have scalability issues and that approximations are needed to solve these problems. And also successfully has been used model predictive control. Here, however, that MPC may require potentially heavy online computation. So in summary, we can state that finding safe control laws is challenging. And the question that we asked was, can we leverage data and use machine learning to learn safe control laws? And this brings me to a bigger point that there's basically a great opportunity to bring machine learning into control to go beyond the state of the art. In brief, machine learning enables computers to learn from observed data. And as we now really have the computational power, we can process large data sets. Why do we want to do that? Here, for instance, in order to improve the performance of a race car or even safety as we gather more data. But also in unknown and unstructured environments, we need to have learning algorithms that allow us to perceive the environment and operate in it. And there are many exciting opportunities. This is also why there are a lot of recent conferences at the intersection of control and machine learning that explore connections and opportunities. I just want to mention some. Data basically reveals system properties, while in control, we want to enforce system properties, right? Machine learning, on the one hand, can improve models, while in control, we use models. So this can be used downstream, really. Data also reduces uncertainty, while in feedback control, we use feedback to reduce the effect of uncertainty so that this can, again, be used downstream. Okay, but now I want to go back to the problem that I promised to address, how to learn safe control laws from expert demonstrations. And I've shown here 3 safety critical systems that may appear to us at first to be very different in terms of the dynamics. But I'm now going to argue that they share some key properties that lets us reason about them roughly in the same way. First, these examples are really data rich in the sense that it's easy to get access to data that exhibits safe system behavior. So if we think, for instance, of Uber, we know that we have a lot of safe driving behavior recorded from humans that we can use. Second, the dynamics of these systems are really inherently nonlinear and hybrid. So we're dealing with complex nonlinear systems that may potentially even be hybrid, meaning that the motion of the system is described by continuous motion as well as discrete events, for instance, when the foot here hits the floor. And third, and this is certainly a very important part, we have a pretty good understanding of the dynamics and we can accurately model these systems. So what we don't want to do here is we want to use model knowledge as well as the availability of data to learn safe control laws for dynamic systems. Okay, I first want to give you an overview of the approach. Let us assume first that we know the dynamics. We can relax this later, in fact we will, but let's assume for now that the system is described by this ordinary differential equation and that we know the functions f and g, and u is the control input to the system that we want to design. Let us also assume that we have a set of expert trajectories, and these are indicated here by these spaghetti trajectories that we assume to be safe, meaning that they evolve within a safe set here indicated by this red box. This could, for instance, be the red box could be all the positions where a robot does not have a collision. Okay. So what we're doing then is we're feeding these 2 things, so the known dynamics as well as our expert demonstrations, into a constrained optimization problem that I'm going to explain in a few minutes. And we have the goal to learn a safe control law by first learning a function that approximates the operating region of our experts. And this is indicated here by this blue region. And based on this region, we want to find a control law that allows us to always stay within this blue region and hence being safe. The contributions here are that we can learn or show how to learn safe control laws with formal safety guarantees in terms of the density of the data, as well as the smoothness of the system. We show how to handle perception uncertainty, and we can even learn safe control laws for potentially unknown systems and for hybrid systems. Okay. So from now on, it's going to be a little more technical. I'm going to explain control barrier functions as a nonlinear control design tool that is really suitable for our purpose here. Assume again the system as described before with a control input that may even be constrained. And assume a function h here that acts on the state of the system, for instance, the position of the robot. And let now the safe set be defined as the 0 superlevel set of the function h. So all states for which h is non-negative define our safe set, in this case, the blue region. Okay. So now if we want to ensure safety, one simple condition has to hold. Basically, whenever the robot is on the boundary of our safe set, we need to be able to either steer the robot inside the safe set or to let the robot traverse along the boundary of the safe set. And we can formulate this in a mathematical way by saying that for all states x on the boundary, we want that there exists a control input such that h dot is non-negative. And by the definition of the safe set here, this implies safety for us. This intuition can be put into the notion of control barrier function, and we particularly say that h is a control barrier function if there exists the u such that h dot is greater than the negative of this alpha function that acts on h. And this alpha function here is an extended class k function, which is nothing more than a strictly increasing function that is 0 at 0. And the 0 at 0 part is really important because on the boundary of the safe set here, our function h is 0, so that this term becomes 0 and we recover the condition that we stated before. For the particular dynamics that I've shown here, which by the way are model a large class of nonlinear systems, our h dot looks as follows. And the reason I'm showing this is simply because the control input u appears linearly here, meaning that we can efficiently synthesize control laws if h is a control barrier function. One piece of terminology that I'm using throughout this talk, I'm going to refer to this inequality as the CBF constraint. So keep that in mind. And as I said, if we can show that H is a control barrier function, then life is great and we have a safety filter. However, the difficulty is that CBFs are in general hard to construct. And we were asking the question, can we instead learn these from data? In order to do so, we of course need to define our data sets. So let's get back to our spaghetti trajectories over here. And let's pick a data point from these trajectories and let's denote it by xi. What we do next is we put a ball of size epsilon around this delta point, here indicated by this orange ball. In fact, let us do this for all data points and let's take the union over them. In that case, we get this orange donut here, to which we refer as the set of safe states. What we additionally need is a set of unsafe states. So we're going to sample states around the boundary of our orange donut. So we're putting these gray rings in here from which we sample states using computational methods, and we label them as the set of unsafe states. And now we're basically ready to write down our optimization problem. One piece of notation first, let us define Q here to be our CBF constraint that I mentioned before. So basically H dot plus our alpha function. And the optimization problem then looks as follows. And I'm going to walk you through it really briefly now. We want to find a function H, like I said, that comes from a certain function class. This could be the set of neural nets. And for obvious reason, we also want to minimize the complexity of this function. Now, what is important for us are these three types of constraints. The first type of constraints acts on all unsafe data points in the gray ring. And what we do here is we push H to be negative. In fact, we push it to be strictly negative and upper bounded by minus gamma, where gamma is a positive robustness slack. For all safe data points in our orange donut here, we do the opposite. We push H to be positive, and in fact, we want to have it strictly positive and lower bounded by the robustness slack gamma over here. So what these two constraints basically do is, in the unsafe region, we push H to be negative. In the safe region, we push H to be positive, and by that, we naturally create a safety barrier by the zero level set of the function H. What we also do is we enforce the CBF constraint here, again, with some slack gamma on all safe data points. Now, let us assume for a second that we can solve this optimization problem, and we have found a feasible solution to this optimization problem, meaning that H satisfies all of these constraints. Then we can say that H is a safe control barrier function if three conditions hold. First, the data points are dense enough. Second, the functions H and Q are smooth enough. And third, the robustness slacks are big enough. And we can put this into math basically by requiring that epsilon, and recall this is the size of the balls that we put around data points. And this epsilon should be upper bounded by the robustness slack gamma over the Lipschitz constant of the functions H and Q. Okay, so far I haven't talked about how can we solve this optimization problem. In general, this is a non-convex optimization problem. However, if we constrain our function class calligraphic H here in a certain way, we can obtain a convex program that we can solve efficiently. In particular, if we let H to be or to depend linearly on the decision variables and are multiplied by nonlinear functions, by potentially high dimensional nonlinear functions, then we can show that we get such a convex program. And this function phi over here can, for instance, consist of Fourier features. And this allows us basically to model already a very large function classes. However, if we want to use, for instance, neural networks, so a general function approximator, then the optimization problem is in general a non-convex one, and we solve instead a Lagrangian relaxation. So the idea is really to go from a constrained optimization problem to an approximate unconstrained optimization problem by putting the constraints into a cost function. And we do this as follows. Basically, we use the sum over the max functions over here, and we multiply it with a Lagrange multiplier that we want to maximize. Particularly note that if this part of the cost here is zero, it implies that all the constraints or the first type of constraints here are satisfied. And then we're doing this for the second type of constraint as well as for the third type of constraint. And this unconstrained optimization problem can then be solved by, for instance, stochastic gradient descent methods. Okay, so we have implemented this in the autonomous driving simulator CARLA. On the left-hand side, you can see an expert controller. This could be a human. In this case, it's a built-in controller from CARLA from which we unroll data. And on the right-hand side, you can see our trained controller that closely approximates the behavior of our expert. And this is in fact what we want. And for that reason, we also get roughly the same safety guarantees. The cool thing is, since we train in local coordinates, we can even apply the controller on a different road, on a different course, or we haven't obtained any expert demonstrations. And this is shown over here, where the controller, our learned controller, still works. What I've presented so far is the vanilla algorithm of how we can learn from expert demonstrations. What we further looked at is the fact that in reality, in all of the cases mostly, one does not know the dynamics exactly. So F and G in general are unknown. What we, however, have quite often is we have good models F hat and G hat. And under the assumption that we can bound the pointwise error between our model as well as the system by some functions delta F and delta G, we can show how to learn robust control barrier function. In fact, the two videos that I've shown on the previous slides, they have already used or trained a robust control barrier function, because in the autonomous driving simulator, we do not have access to the model and we had to identify it. What we also looked at is if we don't have perfect state knowledge. So in most applications, one does not have access to the state X. What we, however, may have is we may have observations such as high-dimensional dashboard camera images here when we talk about the autonomous driving simulator. And we can show how we can learn from such dashboard camera images, how to learn perceptual CBFs. What we also looked at is hybrid systems and how we can get safe control laws for hybrid systems. And I want to illustrate this in some more examples or simulations. Here, we're again in CARLA, and we have collected dashboard camera images. Actually, we resized them because they're pretty big. And from there, we have synthesized perceptual CBFs. And as you can see over here, the controller is still safe. So it stays keeps the car within the lane. The control behavior gets a little more jerky, though, as you can see here. So this could potentially be tweaked. We also have simulations on a compass gait walker. So this guy here is walking down an inclined ramp, and we can control the guy in the hip as well as in the ankle. So if we don't apply any correcting control action, so no control action at all, then the walker will fall down just after a few steps. So what we did here is we went into the literature and we found an energy-based controller that we used as an expert and from which we unrolled a lot of system trajectories. And from there, we learned a 2-hidden-layer fully connected neural network. And if we apply this neural network, we can see here that the walker walks down the inclined ramp safely. And all the correcting control actions are shown here in green. What I also want to show is the following picture. What we can see here on the right-hand side is the energy-based controller, our expert, and on the left-hand side, you can see our learned controller. Each dot over here indicates an initial condition of our system. So in this case, the position and velocity of the left swing foot. And if the dot is blue, it means that the walker walked from this initial condition 10 or more steps. And if the dot is red over here, it means that 10 or less steps are walked, and we label the walk as unsafe. Our safe set is shown over here. And as we can observe, most of the walks are safe. There are some occasions where we have unsafe walks. This is potentially because we haven't connected enough data, but it may also be the case that there is a visual distortion because we're plotting a 4D system in 2D here. What is interesting, though, is that in some regions, for instance, in this area, our our learned controller is doing much better than our expert, as you can see here, if you compare the region on the right-hand side. And with that, I'd like to conclude the first part of the talk. Just to remind you, what we did was we used expert demonstrations as well as model knowledge to learn safe controllers. What we're interested in currently is how can we learn safe controllers in changing environments. So if we have perception in the loop and the weather conditions change, how can we learn safe control laws under these conditions? We're interested in hardware implementations as well as in learning distributed safe controllers. I would now like to jump into the second part of the talk. And while we so far focused on how we can design safe control laws for dynamical systems, I would now like to shift the focus to the question of how can we assess the risk of AI-enabled autonomous systems and how can we verify their safety. And this is here for unknown environments, complex systems and specifications, and in the intersection of machine learning and AI, as well as temporal logics and verifications. First off, what is system verification? Well, it's quite simple. System verification algorithms check if a system satisfies a given specification. Let's assume we're given the race car over here and the specification to never collide and avoid jerky control behavior. Then what we simply do is we feed these two things into a verification algorithm and we get the answer as to whether or not the specification is satisfied. Now, of course, one may ask the question, why do we even need to verify AI-enabled autonomous systems if we can design them in a safe way in the first place, for instance, using methods that I've just presented in the first part of the talk, right? And there are various reasons, one being that in reality, there are various forms of uncertainty on the real system that may render the system unsafe. Here for our learned CBF controller, I've put some noise on the controller, and then we suddenly see that we have jerky control behavior. But in general, many AI algorithms don't even provide any form of safety guarantees. So here we have a vanilla imitation learning controller implemented, and this controller is clearly not safe, as you can see in the video, and in a few seconds, the car will even collide. And I've alluded to this already before. We also know by now that AI algorithms are fragile, neural networks are not necessarily robust. So there are plenty of reasons why we want to verify the safety of autonomous systems. And the question that I would now like to ask is, can we quantify the extent of safety? And towards answering this question, I'm now going to argue that in the future, we will need to have a principled risk assessment for autonomous systems, and that there's a great opportunity to do exciting research in the future. And this is supported by the National Transportation Safety Board in conjunction with an accident with an Uber accident a few years ago. They have made a report stating that the reason for the accident is basically Uber's inadequate safety risk assessment procedures. And they state the need for safety risk management requirements for testing automated vehicles on public roads. And this has also been acknowledged by the research community here, for instance, by a special issue of the Journal of Artificial Intelligence on risk-aware autonomous systems, to which we also submitted last October. Of course, there has been a lot of verification in the literature, a lot of approaches that I don't want to hide here. There is exhaustive testing naturally, but this, of course, is not really systematic and no risk is involved. There's a large body of literature on model checking and deductive verifications in the computer science community. And here, however, modeling is crucial. I would rather like to use data, and this also does not consider a risk. And more recently, there are works on statistical model checkings. And while these already use data, there's no consideration of risk. Nonetheless, model checking or verification of such systems has been used, for instance, here on the Mars rover, Curiosity in 2012, and also what I did in 2016, verifying this KDH research concept vehicle that competed in a competition in the Netherlands. But in summary, we can state that the quantification of risk is missing. And we were asking the question, can we leverage data and assess risk of these systems? Now, in order to formally talk about risk, I want to define risk measures. And risk measures are defined over a cost distribution. So let's say that the blue curve here is a cost distribution, for instance, the cost of failure. And a risk measure that you may all know is the expected value. It's a risk-neutral risk measure, as well as the worst case. What I now, however, want to argue is that neither of them are really useful in safety critical applications, and that we should focus on tail risk measures, such as the value at risk, as well as the conditional value at risk. I'm not going to give any definition here, but the value at risk at level beta is basically the 1 minus beta quantile, and indicates that the probability of having a cost higher than the value at risk is at most 1 minus beta. So, like I said, I mean, why not use the expected value? I've used an example here from a paper that I found for a race car that states that the optimal trajectory for this race car is the green curve here. And while this certainly has good performance, good average performance, it may not necessarily be safe. So why not use the worst case if we're interested in safety? Well, the worst case in this example may be the blue trajectory here, which will have bad average performance, and but it will be safe. But in fact, if we talk about worst case and autonomous or driving in general, then the best thing we can do is just to stay put and not move at all, right? So my point here is that tail risk measures such as the value at risk or the conditional value at risk can be used as a tuning knob between the average cost and the worst case cost. Okay, so let me give you an overview of the data-driven risk verification framework that I'm going to present in the next slides. What we're doing is we're assuming to have a stochastic system, so the environment and the perception, as well as the system and potentially learned controllers, as well as disturbances, are all lumped into a stochastic system from which we can unroll data and collect data. That's our assumption here. We're also considering specifications here denoted by phi, for instance, safety specifications as well as performance specifications. In general, we allow temporal logic specifications. They're coming from the computer science community. They provide us a systematic way of expressing a broad range of system specifications. And what we're doing now is we're feeding these two things, so collected system trajectories as well as our specifications, into a risk estimation algorithm with a goal to estimate the risk of failure. Now, the first question is, of course, how can we define the risk of failure? And our idea here is to quantify the risk of lacking robustness against failure. And we're considering different forms of robustness, spatial and temporal robustness. Let me just briefly explain to you what spatial robustness means. So here pictorially, in this picture, the blue car wants to overtake the black van, and let's say the system trajectory as follows. Then in this case, the spatial robustness is nothing more than the size of the maximal tube that we can put around the nominal trajectory here without intersecting with a blue car. And as we have a stochastic system, we may, of course, get different system realizations and different tubes for these different realizations, right? And what happens then is we get a lot of robustness values that map for us into a robustness distribution as shown over here, over which we can then define the risk of failure. Temporal robustness is something one is interested in, for instance, in semi-automated warehouses, as well as in autonomous driving, where a lot of agents are involved and potentially humans as well. And the question is, how robust is our system to timing uncertainty? For instance, when a human is delayed or arrives too early. And for illustration purposes, assume that a certain service should be enabled within this time frame. And let's say the service is enabled right over here, then the temporal robustness is nothing more than the distance from here to the closest deadline. Okay, and of course, we have a stochastic system. Again, we may have different realizations that have different robustness values. And the story is the same. These robustness values map into a robustness distribution over which we can define our risk of failure. In fact, we do this as follows. We pick any risk measures. This could be the expected value, the value at risk, or the conditional value at risk, and we wrap it around the negative robustness. Why are we using a negative robustness? Simply because robustness, being robust, is something good for us. So large values are good, so that we have to take the negative robustness as our cost function. Of course, the next question is, how can we compute the risk of failure? And in general, this is difficult. So we can not always compute the risk exactly. In some cases we can, but what we can instead do is we can estimate the risk from data. And this is what I want to show very briefly here for the case of the value at risk. But I'm emphasizing here that you can do the same thing for the other risk measures as well. Just to recall, the value at risk is level beta is just the 1 minus beta quantile. And we can give this a mathematical definition that looks as follows. We basically want to find the minimum alpha such that the cumulative distribution function of the negative robustness is equal to beta. And our estimator looks similar, but what we're doing here, instead of the CDF that we don't know, this cumulative distribution function, we insert an empirical CDF that is estimated from finite data. So these ZIs over here is system data over which we form an average to get an estimate of it. Now, since we're using finite number of data, we're making a small error that we're accounting by this term over here. And naturally, we want that this term is small, which we can achieve, which is intuitive, by observing more data. So if n grows larger, or by accepting a higher probability, failure probability delta over here. In fact, what we can show is that with a probability of 1 minus delta, our estimator is an upper bound to the value at risk. Why are we interested in an upper bound? Well, just because we would rather like to be more risk sensitive than not. Okay, so let me illustrate this in a case study. What we've done here is we use the CBF controllers from the first part of the talk. So with full state knowledge, as well as with partial state knowledge. The partial state knowledge controller here is with perception, as I've shown before. And we've also trained 2 imitation learning controllers with full as well as partial state knowledge. What you can see here is that both partial state knowledge controllers perform really poorly. So each of these figures shows 600 trajectories under each controller. And here you can see there are really wide paths here as well. And the red trajectories here indicate collisions. The full state knowledge controllers here and here, they perform really better. But from these pictures, we cannot really tell which of these is the least risky one. And this is what we want to find out now by looking at the spatial robustness risk based on the crosstrack error. What is the crosstrack error? It's nothing more than the distance of the car to the middle of the road. And we denote it here by C. Okay, so what we're doing now is we're looking at 3 specifications. The first specification is that we want that the crosstrack error is always below a threshold of 2.25. Okay. So what we're seeing here in these robustness distributions is that the green and the red controller perform really poorly. And this is as expected. These are our partial state knowledge controllers. So let's zoom in into our full state knowledge controllers. And the interesting thing that we observe then is that the expected value of the yellow CBF controller here is the lowest, while the CBF controller has some realizations here in the tail that are really non-robust. And this is reflected if we look at the value at risk, where the value at risk for the blue imitation learning controller is lower than for the yellow controller. As we're here talking about the safety critical applications, we can conclude that the imitation learning controller is in fact the least risky controller. Now, of course, one may ask the question, why does the CBF controller, however, perform better on average? And this is what we're now going to investigate by looking at the trajectories for each controller during steady state as well as the transient phase. Okay, so for steady state, let's look at the same specification, but now let's only check the specifications for all times t that are greater than 10 seconds. We again observe that the partial state knowledge controllers perform poorly, so we're zooming into the full state knowledge controller. And now the picture is a different one because clearly the risk of the CBF controller is the lowest, both in terms of the expected value as well as the value at risk. So here we can conclude now that in steady state, the CBF controller is the least risky one. So then the question is, why is the imitation learning controller the least risky one over the whole trajectory, while this CBF controller is the least risky one in steady state? And obviously the answer is in the transient behavior. Here we're checking that the crosstrack error is below the given threshold within the first 5 seconds of each trajectory for at least 5 consecutive seconds. And what we're seeing now here is that the imitation learning controller in blue is the least risky one, both in terms of the expected value as well as the value at risk. So it's the least risky controller in transient phase. In summary, what I've just shown by analyzing these specifications is that the imitation learning controller is the least risky controller in transient phase, while the CBF controller is the least risky controller in steady state. And now going back to these pictures here, we can actually identify this because the CBF controller, if we focus on this part, has more wiggling in the trajectories than the imitation learning controller. However, once we move to steady state, we see that there are very narrow paths of the CBF controller, while the imitation learning controller has more wiggling involved. I also want to show one realization of each controller that illustrates this. Basically, here we see in the beginning, the CBF controller goes way more over the lane than the imitation learning controller did. However, now as we progress, as the cars progress and go into the steady state, we will see that the imitation learning controller here on the right-hand side is performing quite poorly. In fact, we will see in a couple of seconds that the imitation learning controller here is going over the line, as you can see here, while the CBF controller stays safe. Okay, and by that, I'd like to conclude the second part of this talk. Just in summary, what we did, we presented a framework to do risk verification of AI-enabled systems. We defined the risk of failure based on spatial as well as temporal robustness, and we have shown how we can estimate it from finite data. Immediate next steps are, of course, this is so far a verification framework, but we would like to use the insights for risk-aware learning and control, and we would also like to leverage the robustness to address for distribution shifts. For instance, what we can show is that the risk of a perturbed system can be upper bounded by the risk of a nominal system plus the difference in trajectories of these systems. Okay, by that, I'd like to thank you for your attention. These are the papers that the talk was based on, and these are the main collaborators that were involved.